All right. Thank you so much, Moit. Hi everyone. My name is Mayowa Egbewunmi, and I'm an Android engineer with Premise Data. I'm also a community leader with Andela, and I've been with Premise Data for over 4 years now, and we've had to do a lot of code changes and refactoring and upgrade. I'm super excited to kind of share some of the things that we've learned, and most especially how we apply the solid principle to some of our refactoring. And I know a lot of people are aware of solid principle and all of that. But in this talk, what I really want to do is to be able to go into the practical use cases of, when we are thinking of solid principle, how can we apply those solid principles to our code refactoring? And to kick that off, just to give us like an high level of what you should expect in this talk and what the structure of this talk is meant to be. So first, I want to set a foundation on what code refactoring is, and maybe like talk about why we should do code refactoring for our code base. I also want to be able to look into some of the overview of solid principles on the high level. We're not going to go into the details immediately, but once we start looking into the applications and use cases, then we start looking into the solid principles individually. Yep. Let's kick this off. So why do we need to refactor our code? Why does it even make sense to clean up a code base that work? And there are a lot of reasons for us to do this. And when I think about everyday life of a developer and what we do as software engineers, largely a majority of it is involved in maintaining code base, and we also write code, we write new features as well, but we spend majority of our life trying to maintain an existing code base and trying to make sure that everything is working fine, supporting production issues, making sure that there's no bad performance in our application in production. That's majorly what we do as software engineers, maintaining this code base. But however, in the case where this code base become very fragile and possibly even tightly coupled together, then what we see as a result of that is code bugs being introduced, bad user experience at the eventuality, and we see a lot of developer productivity being impeded as a result of this fragile code base. So what happens in the end is we get to a situation where we have maintained these bugs, we have followed up with production issues and the likes, and we landed with the eventual point where we feel like, okay, this needs to be cleaned up, this needs to be refactored. At that point, we start thinking about really what do we really want from a refactored code base. We start thinking about developers' productivity. We start thinking about the code base being maintainable. We start thinking about the scalability of our application itself, which is being able to deploy new and more features to the application, and overall the app performance. But what I would tell you is that just refactoring a code is really not enough, which means that taking the code and rewriting the whole implementation, if we do not apply solid principle when going through this refactoring, it probably means that we have created another mess in a different way. And so it is very, very key for us to apply solid principle to code refactoring. And this can be very challenging, especially when you have this humongous code base that everything is so big and large. And then you are wondering really like, okay, where do you start from in applying this solid principle? Where do you even start in terms of like applying this refactoring and piecing things out within your code and making sure that your code is really better? First of all, let's just remind ourselves what is solid principle, especially for anyone who probably is wondering, okay, what exactly is solid principle? Solid principles are a set of principles in our software development that guides what we describe as a very, very good code base, or what we can use to describe that a code base is scalable, it's maintainable, and then the code base has a lot of quality within it. And there are five of them. And the first one is the single responsibility principle. And what that talks about is you have a class that does just one thing, or you have a function that does just one thing. We'll go into the details of each of these principles one after the other. We have the open close principle as well. We have the lift cost substitution principle. We have the interface segregation and then dependency inversion. I just want you to chill and relax. I'm going to go into the definition of each of them, but as I'm going into the definition of each of them, I'm also trying to like pinpoint practical use cases on how we as a company apply this principle to our refactory. But first off, let's start with what does our application looks like, because this is going to help anybody. This is going to help my language description. I want to be able to use some specific terms. So, and I'll be tailoring those terms to premise app. And on the high level, you can think of our application as three categories. One is the onboarding. We have a marketplace and data collection. What we do at premise is to collect data from our contributor. That's what we do, and then we pay them for providing us with that data. And as you can see, we have this onboarding experience that contains like the login, the sign up, and every other flows within the onboarding. So we have it like that. And then we have a marketplace where we are able to distribute tasks to our contributors. That, I mean, you can think of tasks as also as a surveyor as well. And we have different kind of tasks, tasks with different kind of constraint and requirements around it. And on the other end is the data collection, which is like the contributor taking these tags and then providing us with data that we have requested for. So that's what we do at premise, and that's like the high level overview of what we do at premise. Now, we have done a lot of refactoring. I joined Premise as far back as 2019, and since then we've been upgrading the code base. If you look at these are just like some high level ones that I decided to like pinpoint in this slide. You would see here that we have our build infrastructures have been refactored. We migrated a lot of that from Groovy to Kotlin Kotlin build script. And then we also have like our reward experience, which is like the payment experience of our application. We have the job manager as well that does the background job of uploading the data that is being collected by our contributor. Our analytics system has also been upgraded as well. I remember my colleague did a talk on analytics infrastructure of our system at the last NYC talk last year. So that's something you can look up that as well. But we've been doing some of these upgrade within our application. And but for this talk, I just want to target two of them because time will not do me to be able to look into each of all of this refactoring. And those two will be modularization and then map infrastructure. So a lot of what we do at premise involves map usage as well. So those are the two things I would like to get into. So let's discuss the modularization of our premise app. I will start off this by looking into the underlying problem and also discussing how we arrived at a very good solution. So first off, you can think of this as what the high level of our application modules looks like. So everyone has like the app module in their code base for every Android application. And in that app module, all the onboarding experience, the marketplace, and the data collection were all sitting in the app module. And that's the way it looked for us. And we have a bunch of other shared modules, which we can also think about as utility modules. Some of them as like the shared preference module. We have a monitoring module, data collection, or maybe it's even like a feature flag. So we have those bunch of modules that are called utility modules around the application. But really, the core part of our application, the features that we build and develop, we're all sitting in just one giant module, which is the app module. And the challenge with this is that this is not solid. This is not good. And one of the principle of solid principle that it kind of fails at is the single responsibility principle. This really fails at single responsibility principle, and I'll try to help us understand why it fails at single responsibility principle. So thinking about this, before I move to the next slide, number one, which is that we have the app module, and then it has all the packages inside of it. All our features all sitting in the app module for this application. And I've mentioned that it fails at single responsibility principle, and that's just because we have a lot of different responsibility that these features are having to do, and all of them are just sitting within a single module. Let's look at what single responsibility principle says. Single responsibility principle says that classes, maybe modules or functions uh, that are related should be grouped together. And that's what single responsibility is all about. So if you have a class, the functions in the class should be related to together. The function, or if you have a function that you've created, then the implementation details of that function should be consistent in terms of what it really means. That's really what single responsibility principle really entails. And when you think of it, the idea is that we want to bring things that are really related, bring them together and make sure that they are grouped together, and make sure that things that are not related, or maybe they have a lot of invariance around them, make sure that they are decoupled from each other. The core goal of single responsibility principle is that we're able to achieve low coupling, which is like mixing things, invariance things together, and also be able to achieve high correction, which is being able to bring similar things and group them together in order for the consistency of how we reference our code base. That's the idea of single responsibility principle. And we've identified that from our own code base, the app module was not obeying the single responsibility principle, which is you have an onboarding feature, you have a marketplace, and data collection. Those are like giant stuff, all just sitting within the app module. So we have an opportunity, and the opportunity is that we can modularize our application by trying to decouple the onboarding, the marketplace, and also the data collection. At least for a start, decouple it at that high level. And those are the opportunity that we have. But before that, we need to also consider some certain things that we need in terms of building more shared models. Because as a then we had this app string that was sitting in the app model. So the first thing we had to do is we created tech dev to start pulling out some app string into their own module, and then we call that common strings module, where every strings within our application is sitting in its own module. And the other one is, we have some other test helpers as well for our app. We decided to move that into its own module. And then, part of what came out of this modularization is the need for Android-based module. And I'll go in detail to what Android-based module entails and some of the challenges that we had with Android-based module. But overall, we'll look at this and we say that, okay, there's an opportunity for us. Yes, we want to take advantage of this opportunity. The first question that came to us is that which one do we really want to do first? Do we want to pull out the onboarding? Do we want to pull out the marketplace or the data collection? At least we can't do everything at once. We have to do them one after the other. And then we made that decision based on the core value of what we are getting uh, out of each pieces of the application. And if we look at our onboarding, it's a core part of our application. It's very, very important. But the point is it hardly changes. And except if something bad happen, that's when we have to go there and fix things. It's important that we also modularize it, but it doesn't look like it's the first thing that we should focus on. Eventually, we decided to go with the data collection modularization for this, because we feel like there's an opportunity for us there. Looking at the data collection, we decided that, okay, what are the things that are in our data collection? Just to give you an overview of what our data collection system looks like. Number one, it contains like 15 question types. So we support like text question type, video question type, audio question type, any kind of question type, up to 15 of them. It has this inbuilt QC and monitoring around it. It has this support for constraints and predicate, state management and restoration, which is like persisting data in the storage. And also we have this navigator system to navigate from one question to the other. So what should we focus on? Because data capture is also very, very big. We said, okay, the right thing for us to do is that let's pick the 15 question types that we want and decide to translate that into 15 modules, which will help us achieve the first principle of single or solid principles, which is the single responsibility principle. Take those 15 question type, put it into each of their individual module. And when we do that, what does our architecture looks like? We have this app module, and then we have like the data collection core module itself. And that core module is depending on a question type module. And like I mentioned, we have up to 15 question type. I have represented here just like 4 question type. So we have about like 15 modules, and each module representing a question type. From there, we realized that we're going to need a data collection shared module, which is that module where we can put in dependencies that are shared between all the question types. And aside from that, we also realized that we needed an Android-based module. Android-based module in the sense where you remember you have this kind of application where uh, you have some dependencies that are used across the whole application, and that dependency is sitting within your app module. And now that we have to pull out data capture into its own module, then those dependencies needs to be in a module that the data capture can inject. So what does the challenges looks like for this? Let's look at what the challenges look like. The first challenge that we realized with Android based model is the problem of cyclic dependency, and I mentioned that not too long ago, which is the fact that if we have the dependencies that the data collection core module or the data collection shared modules are going to be depending on are still sitting in the app module. We can't inject the app module into the feature module. That is not even possible. So if we would have to solve that, then we would have to like pull out all of those dependencies out of the app module and put them into a module that every other modules, like the feature modules, can use. But the thing that we realize from this is the fact that as we move one dependency into a shared Android-based module, realize that there are also dependencies that dependency depends on. Okay, look at the example that I have here. So we have, say, for instance, the data capture manager, and that data capture manager can be moved to maybe like the data collection shared module. But the thing is, data capture manager depends on Google location provider, and Google location provider sits in app module. Fair enough, we decide that we want to move this Google location provider to Android base. But what we realize is that it's also depending on permission util. So before you know it, you're already running into a rabbit hole where you're having dependencies of dependency of dependency. Remember, in the first place, I told you what our modularization first goal is, which is to kind of like modularize our question types. So before you know it, you realize that you are moving pieces and moving pieces into the Android base. So when you think about this problem, it also presents another opportunity for us. And what are the opportunities that are there? The two other principles in Solid. The first one I would say is the dependency inversion. The other one is the interface segregation. The question is, how did we use these two principles to solve the problem that we're having with moving shared dependencies? Before that, I would like to kind of like do a review, just kind of like do a summary of what dependency inversion really means. Dependency inversion principle states that the high level modules, or maybe the high level class, should only have to depend on abstractions and not concrete implementation. The reason why we had that problem that we had is because we had a Google location provider, or sorry, let me say task capture manager, that was depending on Google location provider, and then Google location provider was depending on permission util. Those are like the concrete implementation of them. In reality, if we're supposed to obey the solid principle, they shouldn't be depending on their concrete implementation. They should be depending on their abstractions, or maybe the interface or their abstract classes. The other thing I would like to call out around dependency inversion is the fact that it helps us to build a more testable code base. Because by the time we start putting abstractions or injecting abstractions rather than concrete implementation, then it means that we can mock those abstractions in our test classes. So what does this look like if we have to solve the problem of dependency inversion? So what that means is that the first thing is that we create an interface for Google location provider. Let's say we call that location provider itself. And now Google location provider is extending or implementing location provider. It has two methods inside of it. We have the get location and the log around it. It's very simple, it's brief, it's straightforward. Now you see here that the data capture manager is no longer injecting Google location provider. Now it's injecting location provider. What we can achieve with this is that if in a situation where migrating Google location provider into the Android base becomes a ripple effect for us, we can choose not to focus on migrating it for now, but rather try to create an abstract implementation of Google location provider, which is the location provider, put that in the Android base, and have Google location provider implement it from the app module. So we know that from the Android base, we can inject location provider to any dependency anywhere that needs to take this. So that was what we did using dependency inversion. But that's not all. If you look at this closely, we have a location provider that is taking Google get location as a method and it has a log. But one thing that we can as well do here is to try to take this further and leverage on the principle of interface segregation for this. Let's see what interface segregation principle says. It says that software components should not be forced to depend on interfaces that they do not use. What does this really mean? If, say, for instance, we have a class called employee, and you have another class called manager, we know that both employee and manager will do some form of work. So they can have an interface that shares work around them. But a manager would do more, has some other works that an employee does not do. Take for instance, and the manager would conduct performance review for the employee. The employee should not be forced to depend on the method performance review or whatsoever. Only the manager should have to depend on that. So what that means is that if you are thinking of how to apply interface segregation to this, it means that we have to decouple the interfaces into multiple and have the concrete implementations extend the particular interface that they really want. And that's what interface segregation is all about. In our own situation, how does this really apply to us? Let's go back to the example of location provider that I mentioned. So here we will not see here that we have extracted out the log method out of the location provider. And this is probably not the best example because it can easily be seen like a boilerplate or whatsoever. But let's just use this for the principle of just following the consistent line of thought for this talk. And we have location provider, and now we have location logger. Maybe we in our system we just want to log in the debug part of our application as opposed to logging in the release. Of course, we have Timber that can do all those management of logging for us. But we decide to build this logger that is only necessary for the debug app. So what does this mean? Now we can have a Google location provider that depends on location provider only. However, we can also decide to say we build a loggable Google location provider, which is the one that does the login and not just get location as well. So we can do login by extending location logger, and maybe it's just print some nice formatting for login and all of that. So let's just do a quick recap around this. We started with single responsibility in order to achieve the modularization. Next, we realized that, when doing the modularization, we needed to apply the principle of dependency inversion. And while implying the principle of dependency inversion, we see that there is an opportunity to even make the code more cleaner, more or improve the separation of concern around the code. Then we applied interface segregation for this. I will mention that it's not in all cases that we apply the interface segregation principle, but in situations that it needed, we used it definitely. So after using all of this principle, what does our code base looks like? Our architecture looks like this overall. We have the data collection module that now extends, that has a bunch of child modules inside of it. That has 15 question types. Each of those question type is now a child module, and then you have a data collection shared module. While we were doing this work, some other work were going on for marketplace as well, and also our reward system. So now, as it stands, we only have the onboarding, which we've started as we took out some feature out of the onboarding as well. How do we summarize these principles, the three principles. Single responsibility principle is not just applicable to classes and functions. We shouldn't just think about it for classes and functions. We can also apply it to modules as well. When modularizing a large monomodule application, we should think of dependency inversion to solve the problem of cyclic dependency and the likes. And we could as well take advantage of interface segregation to improve the separation of concern in the code base. So that's it for use case one, which is modularizing premise app. Let's look at the second use case, which is the refactoring premise map implementation. When we're thinking of refactoring premise map implementation, first of all, let's think about what are really the things that we're doing with map within the application. So like I mentioned, we have a lot of constraints when our contributors are collecting data within our app. So we could tell them to go to a place and then it's area constraint. It could be just location constraint or whatsoever. But the point here is that we have quite a number of places within the application where we use our map feature. We have in our marketplace, we have in our data collection as well, we have in a summary screen as well. Quite a number of them where we use it. And the use cases are just streamlined to maybe displaying map types, displaying polygons and clusters, or maybe even a static map. But we had challenges and we had some problems that we wanted to solve around it. The number one problem we wanted to solve was the issue of cost. We were paying a lot for map usage, and this was going to over like $100,000 yearly for map usage. The second one was around like the team velocity around building map-based feature. We realized that sometimes we get very slow when we need to deliver a feature that requires a map implementation. And this is not something that is surprising, and it's just based on how we implement the map details within the application. But before we go into say, okay, we want to refactor the map details in our app, the first thing we needed to do is to find a cheaper alternative. And I don't want to confuse anybody in this talk, and I'm not even trying to sell maybe Google Maps or Mapbus. But the point I just wanted to realize is that we spent our time, I want to convey here, is that we spent our time trying to identify which one is cheaper for us, especially based on our use cases. And our use cases realized that, okay, Google Maps was cheaper for us. What I actually do also realize is that if we had to be using maybe the address resolution feature of Google Map, or maybe we are using the navigation feature of Google Map, we'll probably be paying more in Google Map than Mapbus. It depends. I'm not saying anything for certain yet. But here we realized that we could save all the $100,000 we were paying in Mapbox. So there's an investment opportunity for us here. And now that we've identified this opportunity, what can we do next? The next thing we can do is to say that, okay, now that we have an opportunity to re-implement our own map implementation details, how do we want to think about the infrastructure of our map-based system? We identify the problem that we currently have. The primary underlying problem that we had is the fact that every time we have to implement a map feature within the application, we always have to go through the whole same step of initializing a map bus and a map view and doing the whole setup within each of those screens that we had. The other part of this problem, which is clearly visible here, is that we are exposing our high-level application or the high-level part of our application to a third-party library. So which means that if we have 15 screens that are using map-based feature, we're exposing our app directly to Mapbus directly. So if we have to change any stuff, or maybe we even have to migrate away from Mapbus and then keep the same implementation details, we have to go to each of those screens to start doing the migration. This is not solid. This has a problem. And the two problems of solid principles that were identified were the open-close principle and the lift-cost substitution principle. Let's refresh our brain on what the lift-cost substitution principle says. It says that if you have a class, a subclass X that depends on a superclass T, then if we have to replace our subclass S, if we have to replace our superclass T with an object of our subclass S, then our code should be fine. It should work. There shouldn't be error, which means that the superclass T object and the subclass S object can be substitutable because S is extending T. That's what it means. The other part to this is that let's say that we have the S1 class and the S2 class that are both extending T. If S can substitute T, it means that S1 and S2 should be able to substitute each other. And that was the opportunity that we realized with this principle that, okay, we can have a Google Map screen, sorry, a Google Map SDK implemented, and we can have a map bus all implementation details. Maybe for whatsoever reason, we want to test the both map SDK in production. We want to see which one user are having better experience with. It means that we should be able to just swap each other, those two SDK for each other within the high level part of our application. So what does this look like in practice for our code base? In practice, we are saying that Google Map, let's assume that we have this Google Map class and then we have this map bus class as well. Now, what we've done is that we say we create the interface premise map that is able to that can be extended by Google Map and Mapbus. And let's say the only method there is just draw elements for it. Really, when we think about Google Map is all about using the Google Map SDK, and within the SDK you have a view element. So if you look at just thinking about what I have here in terms of sample code, you can see a case where I will start inflecting the Google Map view within the SDK or the map bus view within the SDK in this class. But the cool thing is I don't have to do this class thing anymore. Why? Because we have moved to the compose world and I can all implement this within a composed architecture or a composed system. So what this means is that we are now thinking about how we can apply the lift cost substitution principle within the composed architecture. And what does that look like for us? This is what the architecture looks like for us. Then we have this Google Map composable. And then let's say in a world where we have to reintroduce Mapbus composable, then we can have this structure as well. The point here is that we can either use Google Map composable or use Mapbus composable and have either of the two of them depend on our premise map view model. So it shouldn't matter within the view model what composable is using it. The point here is that it can dispatch an event, it can emit an effect, sorry, it can receive an event, it can emit an effect, and it can expose a state that can be collected as well. And at the lower level of those composable, you have the Google Map util that contains really the core implementation details of using some of this composable. The idea is that we want to be able to get to a place where Google Map composable and premise map composable should be closed for modification. And I will explain that very clearly, what I mean by closed for modification for that idea. But before that, let's now look into the case of, in a situation where we have to now use Google Map composable and Mapbus composable. We know we have Google Map composable and Mapbus composable, but should we really depend on them within our high-level screen? So if you have 4 screens or maybe 15 screens or 20 screens, we would have to depend on each Google Map composable or Mapbus composable. Really, that's not what we want. We want to be able to make sure that if we have to switch anything, we are switching the minimal thing as much as possible. So when we realized that opportunity, we decided to introduce another higher level in between those composable. The first higher level that we introduced is the premise map composable. And what does this mean? This basically contains our basic map-based feature that can undo all of those map usage that we use in our application. And let's say we have 3 screens that can easily use premise map composable for us. This is really cool. This makes sense, which means that we don't have to dispatch Google Map composable across all those 3 screens. We just have to use premise map composable. So in a way, we are hiding the whole implementation of Google Map composable and just focusing on premise map composable. The other part to it is that there are special cases for this. Cases where, if you look at our marketplace, it has some clustering around it, and we don't want to bloat our premise map composable. Then we decide to focus on building another specific map composable that can as well maybe like inject Mapbox or Google Map as well. So that was how we landed with this architecture, which is that okay, we want a reusable map composable that can take any SDK map that are out there. And then if the use cases are specific well enough, then we only have to worry about creating a special map composable for that. But there's also something else that we need to think of. When we are using premise map composable, there are situations where, let's say for instance, map screen 3 needs to do a special side effect when a map event X is being emitted. So how do we ensure that we don't have to change map screen 3, or we don't have to change Google Map composable, or maybe the Mapbox composable, just because we have a map screen 3 that needs to do a special side effect or a special work. So, and that's where that actually leads us to the open close principle that we're talking about now. The open close principle would help us understand that really, if we have to change any, if you have to do a special side effect within a specific screen, then we shouldn't have to like worry about the lower level composable, which is the Google Map composable, and just focus on the premise map composable itself. And that's where the open close principle comes in, which says that we can have a class that is open for extension but closed for modification. It's not that the modification cannot come in. If there's a bug, we can modify it. If there's an issue, we can modify it. If we have to upgrade the SDK, we can modify it. But if a change needs to happen just based on specific use case of a screen, then we shouldn't have to worry about changing things on the lower level composable. We should probably just think about it from the premise map composable. From an implementation perspective, what does that look like? So we can see here we have the Google Map composable, and then Google Map composable, if you look at, after we initialize the map view, then the map view can set an event listener. And once there is an event, we dispatch the event to the premise map view model. Now, premise map view model takes in the event, and let's look at what premise map view model does with the event. Here, premise map view model contains a bunch of effects and then event and state. But what I want to pinpoint here is that it's able to accept the incoming event. And what it immediately does is to dispatch the event to an external flow, to a flow that is exposed out, which means that any composable or external view that needs to listen to this event can easily listen to it. And it also has this effect thing where it's able to take an incoming effect from maybe the screen and then pass it back to the map as well. So the map can do that special effect. So that's how our premise map view model looks like. Now let's look at what our high level premise map composable and how it looks like, and how it uses the premise map view model. So it has this premise map view model, and all it basically does is to listen to the map events. It can collect them, and then because we already have this constructor injection or function injected into the composable, which is the unmap tapped, then we can call that function and execute that function. That function is basically coming from the screen that is using premise map composable. And if you see at the bottom there, we have the Google Map composable that is being used to render the Google Map use case for this, or the Google Map rendering. So finally, we have this screen, for example, a Mapbox screen, and then a sandbox screen, and then it's using premise map composable. And now it can do the special implementation that it needs to do. And the way it does its special implementation is to delegate the event that it has received to the sandbox view model. The sandbox view model does a bunch of side effects and all of that. And then we are also listening to the effect, or we are collecting that effect here in the composable. Yeah. And then what we can do here is that whatever effect that is being emitted, we can pass that effect back to premise map composable. Sorry, the premise map view model in this case. So you can see here that the levels of communication between Google Map Composable, the view model, premise map view model. You have the premise map composable, and also the screen that consumes all of this in eventuality. And that's how we're able to, in reality, kind of make sure that the Google Map composable is closed for modification as much as possible, but it's also open for extension or things that needs to happen as a side effect for us. And that was how we're able to kind of refactor that and make sure that we are obeying one of these solid principles. I'm wrapping up my conversation. I talked initially about the modularization that work that we did, where we talked about the single responsibility, we talked about dependency inversion, and we talked about the interface segregation for that. Now, in this case, we can see here that we have been able to apply open close principle uh, to our map refactoring. And one of the things that strikes out for me is the fact that we shouldn't just think about open close principle as just inheritance and polymorphic behavior. We can think about it in different way. We can think about its application in dependency injection, or we can even think about its application in nested composable. We can think about it in those ways as well. In our own case, we applied it with nesting composables and the likes. The other part of it is that we refactored our code base in such a way that we are no longer depending on third-party SDK directly. Now we have created an abstraction or a layer at the top that we can use directly on our screen. So rather than having the map SDK or the Google Map SDK all littered all over the high level part of our application, now what we have is we have the premise map composable and also special or specific map composable that is being used at the high level part of our application. That kind of like summarize how we're able to take the solid principle within our application and then apply it to some of the refactoring changes that has happened so far at premise. Thank you, and that will be all.
Sorry, I forgot to unmute myself. Uh, okay, that was really wonderful. Thank you for explaining how to refactor code and also giving a very practical aspect to solid principles and how we can leverage this. Um, my Mayowa would be here with us for a few more minutes. So anyone, if you have any questions, do pop into the chat. He'll be more than happy to share his views around it. In the meanwhile, while we're expecting for questions to pop in, can you just give any practical advice, like you felt that, yes, apart from what you said, there's some other few bits and pieces which you felt, yeah, this is very obvious, but people don't do it in general?
Yeah, I think that if you have to think about some obvious things that people don't do in general, I think number one is probably would be maybe the interface segregation within a solid principle, and that's because it can easily be thought of around like maybe we are doing a lot of boilerplates within the code base, and then it probably doesn't matter to do all of that boilerplate. The another thing that I can think of around something around what people don't do in general could be maybe people could be very reluctant to getting into modularization or trying to modularize the code base very further. And what I realized is that not a lot of child modules is being used when modularizing. It's probably just like high level. And what we're able to do in our own case is to leverage on child modules in order to like collate related things together to themselves. So I think those are the ones that kind of like strikes my mind when it comes to like this solid principles. Like maybe people don't use a lot of interface segregation in most cases.
Okay, thank you for that. I actually, this kinds of remind me one particular instance few years back when Google Map SDK was crashing, and it was crashing for everyone throughout the globe, and that also crashed our app. And we were in a very tight situation because we practically can't do it anything, and our application was map intensive. So
Wow.
if we would have built it in a better manner that allowed us to have a higher, doesn't expose our higher level architecture with the map directly, as you mentioned earlier, would have might have saved us.
Exactly. Exactly.
Yeah. I don't think so. Any questions are coming in. So I would like you to thank you once again coming onto the platform and sharing all this knowledge with us. It was pleasure listening to you. Thank you.
Thank you, Moit.